My name's Laurie Winkless. I'm a higher research scientist at the National Physical Laboratory, and my research is focused on thermoelectric materials, which are materials that can capture heat and produce electricity. We're looking at ways to capture some of the waste in industry and turn it into something useful. So a good example is probably the car. About 3/4 of the energy you put into your car is wasted, and most of that is in the form of heat. So we can use these thermoelectric materials, possibly on the exhausts of a car, to capture some of the wasted heat, and that transforms it into electricity, and we can use that maybe to charge the batteries up in your car. So my research is to look at the feasibility of these materials, to understand how they really work, and to try and make them useful to industry. We know that this effect already exists, this turning heat into electricity effect. It's been known for about 50 years actually, even longer. But what we're trying to do is to really understand what's happening on the nanoscale. So we're trying to understand how heat really flows in between atoms and how electricity in the form of electrons flows on that scale. And once we understand that, we can maybe make these thermoelectric materials a little bit more efficient. Measuring temperature is something that we take for granted. We think about thermometers, thermocouples, they're things we use every day. But on the nanoscale, we need to get into a very small area and to understand how heat can flow across a small area. And to do that, we need to look towards nanotechnology. One of the techniques we use to look on the nanoscale is the atomic force microscope. But in its basic form, it's an old-fashioned record player shrunk down to size. So it's a long lever and a point at the end. The lever's 50 microns-ish long, varies, and the tip can have a few atoms at the end, so very, very, very sharp. And what we do is, just like a record player, it will move across a surface that we're interested in, and it will respond to any changes, any bumps in the surface by moving up and down in response. Now that's very hard for us to see visibly, so what we do is we shine a laser onto the back, that amplifies the signal, and line by line we'll produce a scan of a sample. And if we want to, we can apply things like a temperature gradient, we can apply a magnetic field, or we can measure magnetic materials, we can apply a voltage, we can look at electrical conductivity, all using this incredibly small tip. On the screen here, you can see two images of graphene. So graphene is just a single layer of carbon atoms. And it's interesting because it has really unusual electrical properties. And the two images that we can see here, this one is the topography image. So this is just the feel between the atoms at the end of the tip and the atoms on the surface. It's just feeling that force between the two. It's a picture, effectively. And the one on the right that we can see here is an electrical image. So it's applying a voltage to one of these tiny probes and seeing something electrically. So not just feeling our way, it's actively getting something electrical. This thermoelectrics project that we're involved with is actually a huge European project. And we don't just have car companies on board, we have companies like Siemens, for example. They're really interested in how heat is transferred through electronics, for example. So when you have your laptop on your knee and it runs hot, that's actually wasted energy from the battery heating up the electronics, and it's not actually making your laptop work any faster, it's just being wasted. So maybe there's an opportunity to use thermoelectric materials to capture some of that heat. And power companies, you've got power plants, they waste a huge amount of energy, more than your car would waste, so they're incredibly wasteful. So there are lots of companies, particularly in the UK, looking at trying to use thermoelectric materials to capture some of the heat that they throw away normally.